This question is on forces and motion. A girl on a sledge is moving down a snow slope at a uniform speed. Draw the free body diagram for the sledge at the position shown on the snow slope. Okay, so we've got the sledge going here. Now, what forces are acting on the sledge? Well, first of all, there's going to be some friction with the slope. Let me draw the sledge so it looks a little bit more realistic. There we go. Also, there is going to be the weight of the sledge, weight or mg. And then finally, there's going to be some sort of reaction force from the snow. Now remember, the reaction force is always at 90 degrees. It's always perpendicular to the surface. So the reaction force is going to be pointing out there. The weight is always vertically downwards, and the frictional force is always opposing the direction of motion. So the sledge is moving down the hill that way, and so the friction must be moving up the hill that way. There is no thrust force pushing down. This sledge doesn't have an engine in it. The sledge doesn't have, she's not pushing along the floor, so there is no forwards thrust force. So these are your three forces. Okay, after leaving the snow slope, the girl on the sledge moves over a horizontal region of snow. Explain with reference to the physical origin of the forces. That means where do the forces come from? Why are there forces there? Why the vertical forces on the girl must be in equilibrium as she moves over the horizontal region. Okay, so the horizontal region, the vertical forces must be in equilibrium, because if the forces are in equilibrium, then there is no vertical acceleration. So she's not accelerating upwards, she's not accelerating downwards, she's not leaving the ground, and she's not sinking through the ground, she's just moving horizontally. Now, with reference to the physical origin of the forces, what does that mean? Well, it means that the weight downwards must equal the reaction force upwards. Okay, then moving on. When the sledge is moving on the horizontal region of the snow, the girl jumps off the sledge. Now here they give you a velocity of the sledge, they give you a mass of the girl and the mass of the sledge. So we've got two masses and a velocity. Now that's your first clue that this is a conservation of momentum question. So momentum equals mv. So m1 v1 equals m2 v2. Now we need to think carefully about what's happening. So before we're trying to find the speed of the sledge immediately before the girl jumps from it. So we've got v1 is what we're trying to find. m1 is when they're both together, so 55 plus 5.5, so 60.5 v1 equals the total momentum afterwards. So there's two things moving. However, the girl has no horizontal velocity after the jump, so we're only talking about the horizontal direction. So the girl has no momentum afterwards, so this is just the momentum of the sledge. So the velocity of the sledge immediately after the girl jumps off is 4.2 meters per second. The mass of the sledge is 5.5. So if we solve this for v1, it gives us a velocity of 0.38 meters per second. Now the girl chooses to jump so she lands on loosely packed snow rather than frozen ice. Why does she choose to land on the snow? Well, you don't get any marks for saying things like the snow softens her landing or anything like that, because you have to explain it in terms of physics. So she needs to stop, so her change in momentum is going to be the same no matter what she lands on. So for the same change in momentum, then what you want with the snow is a longer time. The snow is going to compress, and so the change in momentum is going to happen over a longer time. So the change in momentum equals ft. So with a longer time, with the same change in momentum, the force is going to be smaller. Over the page, we've got the sledge now without the girl on it now travels up a snow slope. So we're going to take some information from the previous question. So the sledge without the girl on it, the mass was 5.5 kilograms. And now it's travelling up a snow slope which makes an angle of 6.5 degrees to the horizontal. Let's draw it up here where there's some plain paper. So we've got 6.5 degrees there. At the start of the slope, the speed of the sledge is 4.2 meters per second. So U equals 4.2. The coefficient of dynamic friction is 0.11. Show that the acceleration of the sledge is about minus 2 meters per second. Okay, it's a show question, so we need to be more precise than that. So we've got we know that F equals ma, and we know the mass, and so we're trying to find the acceleration, so we need to find the force. So what's the force slowing down the sledge? Well, the force slowing down the sledge must be whatever the forces are acting back down the hill. So if we've got the sledge here, then we have, first of all, a component of the weight going down the hill. Now, if that's 6.5 degrees, then the component of the weight going down the hill must be, and that's mg, must be mg times sine 6.5. Now, the other force, so that's the weight component down the hill, downhill weight. Now the other component, the other force that's acting down the slope is friction, and friction is mu times r, and here r is the reaction force. The reaction force is going to balance the component of the weight going that way, so r equals mg cos 6.5, because that's the component of weight going that way, and so R must balance that. So F friction is mu times mg cos 65. Adding this and this together gives you the total downhill force. So the total downhill force, total F, equals mg sine 6.5 plus mu mg cos 6.5, which gives you a total force of 12 newtons. 12 newtons divided by the mass, 5.5. 12 divided by 5 gives you an acceleration of 2.2 meters per second squared. Calculate the distance along the slope at which the sledge stops moving. Well, for this we just need to use some kind of Suvat equation, so let's bring in our Suvat equations over here, and we want to find out S. We've got the acceleration, we've got the final speed is 0, we've got the initial speed, which they've given us in the question, is 4.2, and so we need a Suvat equation with these four in it. So we can use v squared equals u squared plus 2as. Now v is 0, and the acceleration is down the hill, so the acceleration is going to be minus there. So u squared, which is 4.2 squared, equals 2 times 2.2 s. So 4.2 squared divided by 4.4 equals s, which gives you a distance of 4 meters, or to our two significant figures, 4.0 meters.